In this video, I will show you how to simulate the trace impedance over frequency using S11 scattering parameters with KiCad and openEMS. Let's simply start with the simulation process. First open FreeCAD, then create a new project and start the FreeCAD to openEMS macro. If you're new to this channel, please first watch the tutorial video on how to install openEMS. The link to it is in the description. Now let's import the KiCad project. The link to the KiCad project is also in the description. The import progress will be shown in the report view. And once finished, it will show an all done message. Delete the PCB object. Make sure you change to the part workbench and create a new box. Mark all objects in the object tree and change their transparency to 90% so we can see through the items. Now resize the box so it covers the whole copper area with some margin. Make it 0.3 mm bigger above and below the copper trace. The box will represent the FR4 material of the PCB, and we plan to make following stack up. Rename the box to FR4. Alright, now comes the tricky part. If you want to simulate the impedance of such a trace, you have to find a way to remove all reflections from the other end of the trace. One easy thing that you can do is to install a potentiometer at the trace end and trim it until there are minimum reflections. This step has to be repeated for every frequency, which makes it quite time consuming. A faster way is to extend the trace until it hits the boundary and define the boundary as PML layer. PML means perfectly matched layer, and it will absorb all signals that reach it. So it works as an almost perfect termination across all frequencies. Let's add a trace extension by copying the FR4 and resizing it. After that, let's create an input port. Now create a union out of the trace extension and the rest of the copper. Create a simple copy of the fused object and delete the initial objects. Now call the simple object copper. We have now defined all the components, so let's start the FreeCAD to openEMS macro and work through the tabs. We will skip the assignment tab and go back here as the last step. Let's go to the grid tab and define the grid. In the Materials tab, let's add FR4. And in the Excitation tab, let's add a Gaussian excitation and set it from 0 to 15 GHz. Actually, for many mainstream microcontrollers, the port rise time is just around 1 to 10 nanoseconds, which is in the range of 100 MHz to 1 GHz. But keep in mind that the rectangle signal of, for example, a clock line with a 1 nanosecond rise time also has higher frequency components than just 1 GHz. So simulating up to 15 GHz is reasonable in many use cases. Now let's define the port in the Ports tab. I want to inject 3.3 volts. We will skip the lumped parts tab as in this simulation we don't use any SMD components. Let's add a H-field probe to see how the signal travels inside the PCB. In the simulation parameters tab, I will set ymin to PML and keep the other objects as PEC. PEC, by the way, means perfect electric conductor. Let's now finally go back to the Object Assignment tab and assign all the objects. Once done, save the ini file and generate the code. In the Process tab, also generate the S11 code. Now go to the Output folder. The process here is to run the main code, and once finished, you also run the S11 code. Let's open the main code. Now run the code. Close the 3D preview window. You can check the H field dump periodically to check how far the signal already traveled. I will show you now how to watch the signal. Let's type in ParaView here inside the Explorer window. Once ParaView is open, click on Open and select the H field files. Go to Sample 1 and change to the H field coloring. Select the filter Resample to Image. Change from the outline view to the volume view, then select any sample higher than 0 to see changes in the signal. Let's now open the copper layer. Scale it down by 1000 and change the opacity to 0.1. You can change the color of it here. Now select the signal object and change the color range with this button. And now play the animation with this button. Let's save a video file of the animation like this. Select the frame rate of, for example, 30. Here is how the finished animation looks like. As the animation looks okay, let's now run the S11 script. You now already got some results, but this is not yet what we need. To get the trace impedance, close the pop-ups. And now open the generated CSV file. The absolute impedance is shown in this column. Let's make a graph of it. As you can see, it's very unstable. You can improve this layout by increasing the distance of the meander pattern and also by increasing the distance to the neighboring traces. Here is how a perfectly straight trace with the same dimension would look like. Its impedance is almost perfectly flat. The link to both KiCad files and the FreeCAD projects is in the description, so you can play around with the files yourself and find ways to improve the impedance response. We are now done with the simulation. Thank you for watching and see you in the next video.